Hello, everyone. I would like to thank the organizers for inviting me and to thank you all for coming. My name is Itzik Malkiel, and I will talk today about deep learning for the design of nano-photonic structures, a research that was made at Tel Aviv University. So,
hold on, just a second. Is this mic on? Can you hear in the back? So you might just need to go a little bit closer to the mic.
Okay. So, over the last centuries, people tried to see objects that are too small to be seen by a naked eye. For example, at 1665, Robert Hooke discovered the cell by using a microscope that let us see objects that are small as micrometer size. But can we see as deep as we want? So the answer for this question is no. And the reason behind it is that our visual perception is ultimately limited by the diffraction limit, which stipulates that optical information smaller than roughly half of the illumination wavelength is not being is not retrievable. Sorry. Over the past decades, many breakthroughs have led to unprecedented imaging capabilities beyond the diffraction limit, with application in biology and nanotechnology. In this context, nanophotonics, the study of the interaction of light with nanometer scale objects, has had a profound impact on the field of optics by enabling the manipulation of light-matter interaction with sub-wavelength structures. In fact, we can find human-made nanophotonic structure created even before we knew the theory behind the nanophotonics that came up to the world at the 90s. In the figure on the bottom right of this slide, you can see colored glass that can be found at European churches from the 16th century. In practice, this colored glass composed of nanoparticles, and in fact, we can also find nanophotonic structures in nature, such as, for example, on butterfly wings or on chameleon skin. However, the impact of nanophotonics on our daily life has been hindered by a convoluted and iterative process cycling through modeling, nanofabrication, and nanocharacterization. The interaction of light with nanostructure can be illustrated by the following figure. White light, which contain all the colors, interact with an array of metallic sub-wavelength geometries fabricated on a glass substrate. This interaction causes partial current transmission due to absorption, which can be different for each one of the polarization of the electromagnetic field. In fact, these optical properties are dictated by the geometry shape rather than the chemical composition. For example, in this figure, you can see on the figure on the right, you can see three different structures, each transmit different color, although they are all made by the same metal. But due to the diffraction limit, this sub-wavelength nanostructure cannot be observed by a conventional microscope. To date, the approach enabled by the computational tools available only allow for direct modeling, that is, predicting the optical response in both polarization of the nanostructure based on its geometry and material properties. However, the inverse problem, where we would like to infer a nanostructure for an input desired optical response, is much more relevant from a designer point of view and is currently unachievable in time-efficient way. For simple nanostructure exhibiting single resonance peaks in each polarization, one can solve these problems by semi-analytical or by an intuitive manner. However, for a general spectral response associated with more complex geometries, no solution is currently known. In other words, the more complex the optical response desired, the more unattainable the solution of the inverse problem. Shallow neural networks, evolutionary algorithms, and linear regression have gained some success in solving such a task. However, these techniques are still limited in accuracy and practical feasibility and fall short in modeling of nonlinear problems with high complexity of the underlying physical process. In this research, we harness the power of deep learning and show its ability to predict geometry of nanostructures based solely on the far-field spectra. So we have created a synthetic data set using COMSOL multiphysics. The data contains more than 18,000 experiments, where each experiment is composed of a plasmonic nanostructure with a defined geometry, its material properties, and the optical response spectrum for both horizontal and vertical polarization of the incoming field. In our study, we choose a nanostructure geometry represented by a general H form, where each of the outer edges can vary in length, angle, or can be omitted. Such variable geometry is complex enough to span a wide variety of optical response spectra for both polarizations. In this study, we focused on 43 wavelength data points in the range of 600 nanometer to 1,650 nanometer. And in addition, the geometry encoding is a vector of 8 real values that represent the existence of each one of the edges, the length of the outer edges, the length of the inner edge, and the angle of the top left edge. Following our synthetic data set, the direct problem can be considered as a function that receives a pair of material properties and geometry encoding and retrieves a matched horizontal and vertical polarization. Similarly, the inverse direction function is a function that infers a nanoscale geometry from a measured or desired spectra. Notably, in our study, the inverse function receives both the polarization and the material properties, and we leave the topic of predicting the material properties for further investigation. The nanoparticle design process calls for a bidirectional mapping, going from a desired spectrum to a nanoparticle geometry and back. That way, a designer can generate a geometry and match its recovered spectra with the original one. To date, this design capability is hindered by a long trial and error process, and in order to streamline this process, we utilize deep neural networks. In this work, we introduce a bidirectional neural network architecture that embeds the design process into a neural net. The bidirectional deep neural architecture is composed of two different networks. The first network, termed the inverse network, is responsible for predicting the geometry from the spectra. And the second network, termed the direct network, is responsible to predict back the spectra from the predicted geometry. The architecture of the inverse network composed of two different parts, group layers and join layers. Each group layer receives an input from only one group of out of the three groups of data, or in other words, each group of data is being fed to a different group layer. Each group layer consists of three fully connected layers of 100 neurons each. The neurons of the three group layers are then concatenated together to one join layer that is followed by another 8 fully connected layers, each composed of 750 neurons. The last layer composed of 8 neurons that encode the predicted geometry. The second network predicts the spectra, and its architecture composed of 6 fully connected layers, where the first layer receives as an input the geometry encoding, the material properties, and a 1-bit flag that indicates the polarizations that we would like to predict. Every inner layer composed of 750 neurons that are fully connected to the next layer, and the last layer of the network consists of 43 neurons. Each one of them represents the Y value of the transmission graph in a predefined and fixed wavelength values. Since this direct and inverse network can be trained separately to individually solve each direction, and since the nanoparticle design calls for a bidirectional mapping, one may compose the both inverse and direct networks on top of each other, resulting with one model that goes from the spectra denoted by A to the geometry denoted by B and back. While such a composition is possible, it would cause the design process to become unstable. Given a pair of desired spectra, the inverse network would provide a geometry. However, for two separate networks, there is no guarantee that the two spectrum predicted using the direct network applied to the predicted geometry would closely match the original spectrums. In other words, it is likely that there would be a drift when going back and forth. Since during the design process, one is likely to adjust both the geometry and the shape of the spectrum to account for various constraints, this drifting will hinder the effectiveness of the design process. Instead, we propose to train one bidirectional network that goes from A to B and back to A. Thus, we solve the harder inverse problem first, and then, using the predicted geometry, we make sure that the recovered spectrum matches the original one. These two networks are being trained simultaneously, leading to co-adaptation between both networks that eventually results with predictions that are significantly more stable. The training of our bidirectional network consists of two phases. The first we first train the inverse network. In the second phase, we train both networks simultaneously, trying to minimize both the spectrum retrieval and the geometry encoding at the same time. Training such a network requires a dedicated procedure, since the second half of the network is a predicted geometry and not the true geometry that is known to produce the spectrum. In addition, it is worth noting that during the second phase, we perform much more backwards on the second network compared to the first network, and this in order to allow the second network sufficient time to adapt to the first one. In practice, the networks are being trained to minimize the sum of mean square error between the predicted spectra and the geometry encoding to their ground truths. A major advantage of the bidirectional architecture is apparent from the mean square error achieved on the error function in both approaches. The bidirectional network exhibits a significantly lower MSE of 0.22 compared to the MSE achieved by a composite approach. One of the unique properties that we observe is that it turns out that the training of a generalist network significantly outperforms the training of multiple specialist networks. In the nanoparticle domain, the benefit of this anti-specialization strategy is apparent along two axes. First, it is much better to train one network on all types of geometries than to specialize in each one of the subgeometries, even if this means that the generalist network is free to select the wrong geometry. The results shown at the bottom table present that the generalist network succeeded to predict better both the spectrums and, more surprisingly, the geometry shape and properties such as edge length and angle. The second observation is that it is much better to train one network that predicts the spectra for both polarities and accept one bit that indicates the desired polarity than the alternative of training two separate networks, one for the horizontal polarization and one for the vertical polarization. In order to gain insight on the effect of the network depth on the prediction performance, we conduct an extensive comparison between different network architecture. We show that different network depths have a dramatic effect on the results, and we vary the amount or the number of fully connected layers at the second part of the inverse network. And by comparing the results to each other, we see a significant effect on the accuracy of the prediction. We find that the deeper network architecture results with better performance, and the best inverse network architecture for our case composed of 3 parallel group layers followed by a sequential fully connected layers. We demonstrate our bidirectional network ability to accurately predict, fabricate nanostructures beyond the simulations by fabricating a set of different geometries that the network has never seen. We measure the transmission spectra on a home-built reflection transmission setup, and we fed these measured spectra into our deep neural network, and we obtained an excellent agreement between the retrieved geometry and the actual geometry that was measured by SEM, which is an electron microscope. In addition, in the graph, you can see an exceptional agreement between both the measured spectra, which is the black dashed line, and the deep learning predicted spectra and the corresponding console synthetic simulations that we created after measuring the dimensions of the nanoparticle. In addition, we show that our trained deep neural network allow us to find the nanostructure configuration that best interact with a given molecule with target multiple resonances. More specifically, on the first row of this figure, we designed a nanostructure targeted to enhance the interaction of dichlomerathine, which is an important chemical used in industrial processes. On the bottom row of this figure, you can see the design of petalocyanin, that is a synthetic molecule which is also very common in the industry and exhibits both the first row exhibits 3 resonance in one polarization and 2 in the other. And in the second row, you can see also 2 resonances in one polarization, and along with the geometry encoding on the right side of the figure. In addition, it is worth noting that the bidirectional network yields in few milliseconds the parameters shown in the figure, along with match polarization characteristics. This approach can be extended to other molecules for sensing in biology, chemistry, and material science. And in addition, it breaks the ground for the on-demand design of optical response for many applications, such as sensing, imaging, and also for plasmonic-mediated cancer thermotherapy. That's it. Thank you very much. And I'll have a few minutes for questions.
Any questions from the audience?
Can you repeat? Yeah, so that's a good question. The model was trained to predict the response of one geometry. So in fact, during fabrication, we fabricated a set of an array of metallic nanostructures, but the training was done for a single object for every step. We assume that the spacing characteristic, it doesn't affect the spectra optical response. And in fact, we can see it because of the fact that we trained a network on synthetic experiments, and then we fabricated an array of metallic objects, and we saw that we are able to retrieve and both the geometry and the spectra, even though that the fabrication the fabrication process created an array of metallic nanostructures.
Any other questions? Yeah, go ahead.
Yes. That's a good question. From my experience, when it comes to learning, if you have a big data set of phase and amplitude, I think that it would be definitely interesting challenge to see if you can learn these properties using deep neural network. And in fact, I think that it's something that is definitely doable. So we might think about this direction as a further, as a future research. But to tell you if it would be an easy task, it's a good question.
Actually, along the same lines, can you comment on like what? So the network learns something that is somehow generalizable. That's beyond what just the training sets that you do. Right?
Yeah.
You used a finite element method, whatever, to simulate the EM fields from known structures, and then you fed that into the network.
Exactly.
So you learned how to generalize between the mapping of the parameters that you set the simulator and the results that you get. And so what did the network learn beyond what you fed? Is that?
Yeah.
Can you comment on that?
Yeah. So one thing that we understood is that the network was robust for the noise that was apparent in the measurements. So this is an interesting property because if you can see the measured spectra, the black dot lines are really contain more noise than the synthetic experiment. So it's very interesting to see that the network was able to understand or to look beyond the noise and to understand by extracting features of the resonances and the location of the resonances, and to infer the geometry, the right geometries that is very close to the true geometries that we measured by the SEM. So one more thing that we saw is that we tried to see the generalization capability of the network, and we actually elaborated about it more in the paper. And the current approach have some limitation when we try to use, of course, different geometry that are significantly different from the shape, from the H form shapes that we use during the training. In future research, one can think about trying to predict the image of the geometry instead of trying to predict the geometry encoding, and this is something that we are looking at right now.
Any more questions? No, let's go ahead and take it.
Thank you very much.
Okay, thank you. Good afternoon, everyone. My name is Suren Jayasuriya, and I will be presenting our paper along with Dr. Hiro Kubo. This is collaborative research from NICE, CMU, and Arizona State University. So the primary motivation for this work is to capture decompositions of light transported in a scene from illumination source, the interaction of those light paths with objects in the scene, and then capture to the camera. In 2006, Nagler et al. Developed a method to separate direct and global components of light, global or indirect light. Direct light consists of light emanating from the illumination source, bouncing exactly once in the scene and arriving at the camera. And we have seen in the previous keynote the benefits of measuring direct light only for structured light and triangulation methods. Global or indirect light is light that bounces more than once in the scene. In this work, we're actually interested in further decomposing these components because they contain a lot of interesting optical effects, such as short and long-range interreflections, subsurface scattering, and specular interreflection. So to parse these light transport paths, we can further decompose a scene into subcomponents shown here. In previous work by O'Toole et al. And others, specific components like direct and specular, diffuse and specular direct and diffuse and specular indirect components of light transport has been acquired. These methods, these decompositions have been obtained using primal dual coding as well as time-of-flight imaging. In this work, we present a new imaging modality to capture subcomponents of indirect light that are parameterized with 2 degrees of freedom that I will discuss further. This imaging technique exploits the light transport between planes of illumination in a projector and camera rays to acquire indirect light components, specifically by extending the ideas of epipolar imaging introduced by O'Toole et al., and which was talked about in the previous keynote this morning. So again, in our imaging scenario, we have a projector that's illuminating the scene 1 row at a time, which forms a planar sheet of light that's swept across the scene. At the same time, the camera's rolling shutter exposes a row or scan line of the sensor at a time. This combined projector camera setup is rectified so row I of the projector lies on the same epipolar plane as row I of the camera. By synchronizing the illumination and rolling shutter, epipolar imaging allows light that remains on the same epipolar plane to arrive at the camera, which consists of mostly direct light or one-bounce light. By exposing all other rows except the illumination row, one can also capture non-epipolar light, which is indirect. So in our work, we are going to vary 2 key parameters of this epipolar imaging system. Epipolar light, again, is determined by the light from projector row I to camera row I. However, if you change the synchronization trigger signal to be delayed temporally, we can parameterize the row offset from the illumination row and the camera row. This delay captures indirect light that travels from projector row I to camera row J. The second parameter we control is the exposure of the rolling shutter of the camera. This increases the illumination bandwidth that a camera row receives. Note here that increasing the exposure here is not simply changing the brightness. You're actually letting more light from adjacent rows of that projector enter into the camera row. In this paper, we are going to utilize these parameters of synchronization delay and exposure to acquire indirect light transport components. So in particular, we formulate this indirect light transport as a 3D light transport operator. It's between 1D projector rows or planar illumination and a 2D camera ray or pixel. Intuitively, this corresponds to indirect light that is sent out on one epipolar plane and then jumps to another different ray that is captured at the camera. And this is controlled by the delay parameter. So the key insight of our paper is that this synchronized rolling shutter system, parameterized by delay and exposure, performs a type of illumination multiplexing. And there's been work by Schechner et al. And others that show that illumination multiplexing gets high SNR benefits during capture, and then you do demultiplexing in post-processing. Using our parameters of delay and exposure, we can define the illumination bandwidth, the size of the amount of indirect light and direct light we're getting, as the function of the scanning velocity times the exposure time. And similarly, we can define the row offset as defined by the scanning velocity of how fast the rolling shutter is progressing times the synchronization delay. So we can write our illumination function parameterized by these quantities that explains the multiplexing, and we can formulate a forward imaging model that describes the illumination multiplexing as following. I of ST is the intensity of pixel ST is a convolution between this illumination function, parameterized by this delay and exposure of this epipolar imaging system, and a convolution operator, T of V ST. V is the projector row, and ST is the column, and it's a 3D light transport operator. For implementation, we are going to use the same hardware platform, Episcan 3D, which later we'll be showing you a demo here on stage. Again, this consists of raster scanning laser pico projector that's epipolar rectified to a rolling shutter CMOS cameras. Here we have two cameras shown in the picture, but we're only using one camera for this paper. Synchronization is performed via a trigger signal from the projector to the camera. Now, to describe the experimental results from this section, how we do the demultiplexing algorithm to estimate light transport and applications, I will turn it over to Dr. Hiro Kubo.
Thank you, Suren. Hello, my name is Hiroyuki Kubo from Nara Institute of Science and Technology. Firstly, in this slide, we show a stack of images performing a sweep of the parameter synchronization delay while keeping exposure fixed for a scene consisting of a disco ball. Notice how the specular interreflection of the disco ball moves vertically as delay increases, corresponding to indirect light paths jumping from illumination plane to received camera ray. At a delay of 0 microsec, we capture epipolar light, which is considerably brighter than the indirect light component at delays away from 0. We note that such indirect light components are dark and subject to noise due to the low light levels. To increase the light present for indirect component, we can increase the exposure or illumination bandwidth of the rolling shutter. Notice how the amount of specularities increase with exposure time as more indirect light is captured. Okay, so we plot here the light transport components captured as a function of two parameters, delay and exposure. Epipolar image occur on the center at delay equals to 0, and non-epipolar or indirect light otherwise. We note again that indirect components suffer from low light levels and high noise. To solve the problem of increasing SNR while maintaining control over the components of short and long-range indirect light captured, we estimate the 3D light transport in the CM to demultiplex the illumination in post-processing. As stated earlier, we can formalize the light transport between projector row and the camera pixel as a convolution between an illumination function and the light transport operator to form an image for a given delay and exposure. This expression captures the illumination multiplexing performed by this synchronized projector camera system. Using different observation of delay and exposure from the image stack we captured, we perform an optimization algorithm to demultiplex the lighting and recover the 3D light transport operator. This algorithm minimizes a data fidelity term based on our formulation and adds regularization to improve the optimization. The result is the 3D light transport from projector plane to a camera ray. Using this light transport, we can synthesize new images of a scene in post-processing. Here in this scene, we image a translucent wax rose that features subsurface scattering. In the middle is an epipolar image of the rose with a large illumination bandwidth during capture. By estimating light transport from delay exposure stacks, we can synthesize a tighter epipolar image that is removing indirect light from the scene after the image has been captured. One of the benefits of light multiplexing is a higher SNR at capture time. Here we validate this idea by showing our synthetic rewriting as compared to actually projecting a single line onto the scene. Our synthesized rewriting has the same SNR as a long exposure. Our plane-to-ray 3D light transport is very useful for scene analysis. The graph on the right shows the light transport intensities of each pixel with different delays. Please take a look at the green dot on the picture. This corresponds to a direct reflection on the book. In the graph, this green curve has a single peak in the center. Blue dot contains a specular interreflection from a disco ball in addition to the direct reflection. In the corresponding graph, there are two peaks. The orange pixel here on the wax candle features subsurface scattering from the wax material, and thus the shape of the curve is relatively broad. The red pixel on the corner of the book contains diffuse interreflection. In the corresponding graph, the curve is relatively sharper than that of subsurface scattering. Thus, by analyzing the delay profile, we can analyze the light transport effects present in the scene. In fact, we can go further to actually understanding material properties using delay profile. Here we show a set of materials that are visually indistinguishable from one another. By looking at the delay profiles, we can actually recognize these materials, which include fat-free milk, 2% milk, whole milk, toothpaste, and liquid soap. We trained a nonlinear SVM on the delay profile per pixel to achieve over 90% recognition and semantic segmentation. We know that better performance can be, of course, achieved with state-of-the-art machine learning methods, but it is clear that delay profiles provides information of the subsurface scattering for materials, which we use for classification and understanding. Okay, let's take a look at my hand here in this regular image. When the delay is 0, we receive epipolar light from light bouncing off the surface of the skin. With a large delay, capturing far-range indirect light, we do not capture any meaningful light paths, unfortunately. However, with an appropriately chosen delay, we can reveal the hidden structure of the veins inside my arm. Now we are going to show a demo of our imaging system.
So here we have the regular image. So what we have is our pico projector is projecting those planar sheets of illumination, and the camera is synchronized to the rolling shutter is synchronized to that thing. When we synchronize them so that they're tracking equally, we get the direct image. So if you notice here, the specularities on the disco ball are mostly removed, and the wax translucent material is optically black. So this was epipolar imaging, regular. The converse is non-epipolar imaging, where you expose every row except the row that's being illuminated on the projector side. And here we see all the indirect light components with the direct component minimized. Next, we're going to show the effects of delay and exposure, the contributions of this paper in real time. So here we're changing the delay, and you notice as we went away from 0, we lose the epipolar component. But here we're getting indirect light that's jumping from one epipolar plane to another. And now changing the exposure, you notice not only is the scene getting brighter, but we're getting more and more specularities appearing in the scene. And this is all just by adjusting the delay and exposure parameters. And again, as we showed earlier, if you pick the right delay and exposure settings, you can reveal hidden structures, such as the veins. And this is in real time, just by optically picking the right delay and exposure for the system. And in fact, so even for darker skin, you still can obtain some, I can't see, but yeah. I can't. Wait, this side. Yes. So you can still see some things. So even with dark skin, it's a matter of signal to noise ratio. But just by using this optical system, no time of flight system, just by controlling the computational illumination and the synchronized rolling shutter, we're able to achieve that.
Okay, so in conclusion, we showed a new imaging modality to capture and analyze indirect light transport. We demonstrated illumination, demultiplexing, and light transport estimation. Also performed light transport scene analysis and material classification. As a future work, we expect to extend our method to image systems like epipolar time of flight or epitoph. Thank you for listening.
Yes, so I'll repeat the question. So you said when the delay is very small or like far away from zero, you see some flickering patterns or artifacts. That's an effect of the synchronization. So we have to optically, we have to rectify the system. And so any deviations from the ideal rectification will cause synchronization issues. So they're an effect of the synchronization, and it's a hardware limitation.
What delay ends up being good for the arm? That ends up being related to the mean free path of the skin? Is that kind of the idea?
So there is probably a relationship between the transient temporal time of flight. It's basically a minimum bound on if you send light out in one epipolar plane, it must have traveled some distance to come back. So that relating that delay parameter it's not like an exact time of flight. It's more of a minimum bound on it. But what was the microseconds? I think it was 500. Yeah, 500 microseconds. Yes. But relating that back to
really the physical, the spatial separation that's significant, not the timing.
Yes, but space is related to time. Yeah, right. It's just yes.
Through the scans.
But it could have bounced multiple times and then come, or it could have bounced only once or twice and come back. So it's a minimum bound, not necessarily an exact.
Other questions? Okay, let's go ahead and thank the speakers again, and we'll move on.
Good afternoon, everyone. My name is Maeda. Along with my co-authors, Achuta, Kadambi, Schechner, and Ramesh Raskar, we are here to present a novel and unique form of interferometry. We call this dynamic heterodyne interferometry. Yes, I understand that this title has some buzzword, but let me clear this up in the next few minutes. Let me start with interferometry. Interferometry is a wave optic technique that utilizes interference of light wave to capture some information about the world. For example, to 3D scan small object in nanometer, micrometer scale, like this gummy bear. However, the challenge with interferometry is that it requires multiple measurements, which makes it hard to capture a dynamic scene. So when this gummy bears move, interferometry fails to capture it. There's a solution to this problem. A specific setup of interferometry exploits polarization to multiplex measurement in a single-shot manner. Because this setup can capture a dynamic scene, it is called dynamic interferometry. But there's still a challenge in robustness with this existing method of dynamic interferometry. And let me illustrate this by example. Here's a water droplet on a glass slide. Interferometry is typically performed in a controlled laboratory setup. So when dynamic interferometry is performed in laboratory, it succeeds to get a phase measurement of this water droplet. On the bottom image, you can see the high frequency variance introduced by water droplet. But what if there is an ambient disturbance, like flashlight shining an interferometer? Now, as you see in the image, the water droplet is gone. The high frequency variance is lost. It's covered with low frequency bias, and nothing we can do with post-processing can recover it. So we need a new interferometry design. Our technique, dynamic heterodyne interferometry, succeeds to capture a water droplet even then when there's an ambient light. This right image and left image is taken under the same conditions, same setup. So at the top level, we demonstrate an interferometry that is dynamic and robust to ambient biases at the same time. That's our practical contribution. Though this method solves practical problem associated with existing interferometry technique, there's something interesting and unique about this that I would like to share with you. If you allow me to ask you a question, how many of you have seen an interferometry fringe pattern? It's actually, I found this funny because I'm a still undergrad and usually professors ask me questions, but today it's the other way around. Anyway, a lot of you are already familiar with interferometry, fringe pattern. As you see, the brightness changes over the space. This white and black band is called fringe pattern. But in this paper, we are presenting a fringe pattern is different and hopefully something that you might not have seen before. In dynamic heterodyne interferometry, a fringe pattern varies in space, time, and polarization. The fringe varies in space, as you see from the white and black bands. The fringe varies in time, as you see the brightness changes between video frames. And finally, the fringe varies in polarization. Each quadrant video is taken with different linear polarization angle, and they capture slightly different information. This special fringe pattern is the engine that powers our interferometry design. We call this time beating signal heterodyne. Thus, we have dynamic heterodyne interferometry. Our contribution is to combine dynamic and a heterodyne setup in interferometry. Let me summarize those terms again. Dynamic refers to a capability of multiplexing measurement in a single-shot manner. Heterodyne refers to the temporal beating of interference pattern. And finally, interferometry is a wave optic technique to capture information about the world. This is our optical setup. There are some components that I haven't explained yet, so let me walk you through over. In general, our method can be implemented in multiple interferometry setups, such as Mach-Zehnder and Michelson. But today, we focus attention to Mach-Zehnder interferometry setup. How many of you are familiar with Mach-Zehnder interferometry? It's many. So if you don't know, please don't worry. I'll walk you through briefly. In this Mach-Zehnder setup, a beam goes into beam splitter, splits into two arms, and merges with the second beam splitter. You can place an object which causes optical phase shift. And by observing the fringe pattern, we can get information about this object. The core idea in interferometry is very simple. It's just superposition of waves. When waves have same optical phase, they add up together. If the phases are opposite, they cancel each other. In general, the intensity in interferometry is formalized in this way. And there are three unknowns in this intensity, so we need at least 3 measurements. Traditionally, people use 4-bucket trick, which requires 4 different phase measurements that are pi/2 apart. And traditional interferometry uses moving mirror to achieve this phase shift. So you have to wait until mirror moves, stops, moves, stops. And this is why it's hard to capture a dynamic scene. This is where polarization comes in for existing dynamic interferometry technique. This technique introduces 2 circular polarizers in each arm and linear polarizer in front of the detector. I refer to technical details of the polarization and the mathematical formulation in the paper, but let me give you some intuition behind polarization. Polarization is basically specify a geometric orientation of the wave. For example, the light wave shown in this slide is constrained in a vertical plane, so it's called linear polarization. If you have a horizontal plane, wave on a horizontal plane that are pi/2 apart from the vertical wave, this is called circular polarization. Why do we care about this? There's something interesting happens when this circular polarized light interacts with the linear polarizer. Only the vertical component passes through a vertical linear polarizer, while only the horizontal plane passes through horizontal polarizer. And here, the resulting waves are actually pi/2 apart in phase. Again, we refer mathematical derivation in the paper, but in the general case, when linear polarizer angle rotate by alpha, the resulting wave also shift by alpha in phase. In dynamic interferometry, we use circular polarization in opposite-handedness, where the waves on the horizontal planes are flipped from each other. This generates plus alpha phase shift in one and minus alpha in the other after the linear polarizer. Now, we could shift the phase in total by 2 alpha without using the mirrors. We do this by using the linear polarizer. Now, the intensity is a function of space and polarization. In practice, polarimetric camera is used, and this camera has a pixel that consists of 4 subpixels with different linear polarizer angles. And because the phase shift is caused by 2 alpha, the alpha needs to be pi/4 apart, as 4-phase trick requires pi/2 apart phase measurements. Now, let me move on to a contribution. We add temporal beating in this dynamic interferometry setup by adding a acoustic optic modulator, AOM. AOM shifts the frequency of the light by its operating frequency, typically around 80 megahertz. And we use the AOM to generate a low frequency beating in an experimental setup. So why do we do this? We can create 2 waves at different frequencies by operating AOMs at different frequencies. When these two waves interfere, what happens? It produces a wave whose amplitude is modulated by the frequency difference. Combining this with the existing method, now we have intensity that varies in space, time, and polarization. And this is how we get a special fringe pattern we saw at the beginning of the presentation. The benefit of having a temporal signal is that we can take the correlation, so we can reject the noise that are not at the specific frequency. For example, we can remove a noise of DC ambient light. Thanks to the current development of time-of-flight imaging, we have a camera that takes correlation pixel-wise. This interferometer setup is a little ahead of current camera limitations. To fully realize the benefit of our interferometry design, we want the beating frequency to be fast, which I'm going to explain later. So we need to combine existing correlation camera like Microsoft Kinect with polarization mask. Now, I'd like to compare the effect of ambient light in both existing and proposed method. So why is dynamic interferometry susceptible to ambient light? Ambient light has some polarization component. For example, the vertically polarized component of the ambient light can pass through one orientation of the linear polarizer, but not the other. This generates an even distribution of intensity due to the ambient light. To analyze this, let's go into more details. This is how the phase can be calculated by dynamic interferometry when there's no ambient light. When there's ambient disturbance, this phase measurement is screwed up by this red term. To give some intuition, as kappa, the strength of the ambient light increases. This phase measurement is dominated by this red term and become unreliable. Analyzing closed form approximation of arctangent is hard. So let me take first order approximation, a tail expansion approximation, to analyze the effect of bias in both proposed and existing method. Interestingly, there's specific angle, specifically when 2 theta equals to minus delta phi. There's no ambient light bias because the sign goes to 0. However, in general, we cannot assume any angle for the theta, so there usually ambient bias introduced, as I showed in the water droplet slide. The key insight here is that dynamic heterodyne interferometry, a proposed method, can scale the error of existing method by 2 over beating frequency times correlation time. This is why we want faster beating frequency. Current correlation camera can perform correlation at 80 megahertz. So if you take correlation time of 3 milliseconds, this can achieve a dynamic performance and also drastically decrease the ambient bias. Let's see how this screwed up factor shows up as a measurement. Because we want to see how this is screwed up, we take the screw. This is a computer-rendered simulation, and we simulated both dynamic interferometry, which is a prior work, and a proposed method, under the same ambient light condition. As you see, as the ambient light becomes stronger and stronger, the screw is screwed. But with proposed method, screw is not screwed. It shows some robustness to the ambient bias. This plot provides some insight. Interestingly, our method performs slightly worse in a controlled setup where there's no ambient light. This is because heterodyne setup is more susceptible to shot noise due to temporal beating and correlation. Our work is a small step towards what's possible. Of course, there's limitations, for example, the cost associated with additional hardware, or the trade-off in low ambient bias region. But we believe that our technique can perform robust and dynamic interferometry in the wild and potentially expand the range of objects that can be scanned in various fields. Maybe interferometry can come to your dance floor. So far, we have proposed a novel and unique interferometry design, and we showed its practical benefit compared to existing method. We also showed in the theoretical side that the temporal beating and polarization can put together in one single equation. To take a bigger picture, there are many works in computational wave optics that combines computational imaging and wave optics. For example, Professor Warren's group in Berkeley uses diffuser to create light field camera. Professor West's group in Stanford uses wave interference to improve a light field microscopy. Our session chair, Professor Cossard, uses interference to achieve digital focusing, digital refocusing, and 3D scanning. At CMU, Professor Jonas studied a micron light transport. This Gambia is actually from his paper, his work, using interferometry. And my co-author, Achuta Kadambi, used polarization and interferometry to improve the resolution of 3D reconstruction. Overall, I and my senior co-authors believe that what we present here today is a small part of a bigger trend that combines computational imaging and wave optics. And we hope to inspire further unity of these two fields. Finally, I'd like to thank my co-authors, Achuta Kadambi, Schechner, and Ramesh Rasker. They're not only the co-authors, but also a great mentor to me, because this is actually my first conference, and they gave me a strong technical development and also inspiration in research. I'm presenting the poster tomorrow, so if you have further questions, please come see me at the poster session. Thank you very much.
You have some questions? Yeah, go ahead.
That's a big congratulations. So I have one question. So in this, when you're using this polarization camera, you still need multiple measurements. You need at least 2 or 4 screens. So my question is, why not just use a normal camera? What is polarization buying you in this case compared to normal camera? Even there, you do heterodyne, you can take multiple things, even there, you can do multiple things. So should I understand it correctly?
Yes, thank you for the question. So the reason why the polarimetric camera is used instead of the normal camera is from these equations here. Here, the A and constant and the phase delta phi are unknown, so we need multiple measurements to recover the delta phi we're interested in. And the single measurement cannot provide these informations. And here, the linear polarizer mask actually achieves a different pixel. So if a pixel of the polarimetric camera has 4 subpixels with different polarization angle, so each pixel captures 4 different measurements that's shifted in a phase by pi/2. And from using these 4 values, this polarimetric camera can achieve recovery of the phase for each pixels. And if there is no polarization, there needs to be another way, which, as up to my knowledge, is moving mirror. And that mechanical movement takes time. And yes. So, yeah, the polarimetric camera is they use the polarization to capture multiple phase information in a single shot.
Go ahead.
I have a very simple question. So you talk a lot about suppression of ambient light, but normally interferometry is done with monochrome light. So can you use a simple band filter
That's actually a really good question. I was not, to be honest, I've not thought about it. In a way, we know that interferometry is mainly performed in a control setup, but we wanted to propose a method that can potentially move interferometry outside of the control setup. So many different measurements can be taken outside. For example, if needs to be someone needs to investigate the surface of solar panel, but if the sun is very strong, I believe that further robustness can benefit that sort of measurements.
I have a question, which is, so did you think about just implementing this, just using a correlation sensor as opposed? So your paper talks about how the ultimate goal is to develop a lock-in sensor,
Yeah.
which can detect in-phase and quadrature and remove the DC bias.
Yeah.
But did you think about just implementing on a correlation sensor as an alternative? And I guess maybe this relates to Noel's question. Is that sort of breaks the model? You have to have a lock-in sensor that can do the in-phase and quadrature, or you have to have a correlation sensor with multiple measurements. Is that the idea?
The idea is, so there are always trade-offs between individual methods, and I believe the correlation camera needs to take multiple measurements to get 4 phases, whereas so they change the phase, they electronically change the phase, and a method provide optical method way to shift the beating, like temporal beating of the optical signal. So we found it interesting as this beginning, and we also believe that as a trade-off side, this can achieve faster acquisition compared to the electronically like shifting the phase.
Any more questions?
So I have a quick question. So the object you showed in the slide and in the paper seems to be like glass and like which surface is smooth. Have you ever tried to imitate something of the surface not smooth, like glass surface, for example?
Yeah, so interferometry can be very complicated in like many different dimensions, and we wanted to show that. So that's a good question, and we are gonna work on this. But when we capture a surface of the small object, that requires more like a microscope setup. But here we wanted to show the robustness against ambient light, and we found that showing the water droplet example could show the same this effect of a dynamic heterodyne interferometry as a robustness. So that's something that can be improved in this study. Thank you.
I think let's go ahead. We've had a couple questions. Let's move on to break. So we have a coffee break now, and then we'll come back at 3:15. Let's take this to the one last.